Today's lecture is all about the applications of vector-valued functions R of t. So let's make a note right here that today it's about applications of vector-valued functions. I'm going to make it short here as vector functions because they are the same thing. Vector functions R of t. We learned about this R of t on Monday, and today we are going to make use of this and apply it to some real-world applications. So we are going to start with this R of t, and we are going to begin by assigning this R of t to be the position vector of any object in 3D space. So let's start with this R of t. It's going to be assigned to be the position vectors of objects in 3D space. You can use this on 2D space, but when it comes to objects and items, and when we want to analyze the motion of these things, let's stay with the space that we live in, which is 3D. Now that we have this RT as position vectors, it means that we can transform this into the coordinates of the objects. And once we know the coordinates, then it means that we know the locations of these items. Okay, now usually when we want to analyze about any object, we don't just want to know where it is. Location is not enough. We want to know more about them. You want to know how it's moving. Is it still? Which direction is it moving? Is it going faster or is it getting slower? So we want to know more. So this RT is not enough. And that's why today we are going to perform some more calculations on this R of t. Right? And we are going to use the techniques and the procedures in calculus. So next thing we are going to do with this R of t is to use calculus. And we have learned about this techniques in Cal 1, and they have to come back today and get used again because it's going to be needed to change this RT to something else. So we are going to perform some calculations on this RT to analyze motion of objects in the space. So this is the final goal for today. Analyze motions. So this is the keyword. The motions of objects in 3D space. Of objects. Alright. So starting with the position, then we expand it to something more. So let's move down here. So I'm going to start by writing this R of t again. And I'm going to write the components of this R of t as well. This is coming back from Monday. As we know, this is vector functions, so it's going to have components. So let's write the components of this RT. So I'm going to have I, J, and K right here. By having I, J, and K, it's implying that I am working in the 3D space. And recall what we learned on Monday when it comes to vector functions. Each component can change independently and differently. So for each component, it's going to have its own function. With respect to time, at different time, each component is different. And for J component, different functions. And last component, again, a different function, h of t. Alright, so what we have right here is the position vector of any object in 3D space. Make a note right here, this is position vector. Position, or you can say that this is location. And as I told you, location is not enough. We want to know how it moves. So the first thing we can do here is to perform the differentiation. Find the first derivative of this r with respect to time, and that is what you see right here. we differentiate r with respect to time. And what you see, let's make a note right here that this is the first derivative of r of t with respect to time. Okay, and sometimes we can call this as the rate of change. Rate of change of r of t. Yeah, r of t, which is the position. Rate of change of position. Position over time. And of course, this means the same thing, how this object is moving, right? So this can be translated into the velocity. Rate of change of the position equal to velocity. Let's make a note on the left-hand side here that this is velocity. Velocity. Okay. But there is something that you have to pay attention to, is that what you see right here is a little bit different from what you learn in physics, because when it comes to finding this derivative, we perform it on this vector functions. Vector functions. Keep in mind that this time around everything is vector functions. Vector functions. And let's take a look here. If you perform the first derivative here, it's going to be a tight space, but I'm going to try to fit it in. So right here, let's try to perform the first derivative, r prime of t. As I taught you on Monday, when it comes to differentiation, you need to apply this diff to each component separately. So here we are going to get f prime of t I plus g prime of t j plus h prime of t k. The reason that I had to write this down is because I want you to pay attention to what we get right here. What we get right here has I, j, k components. So this r prime of t are also vectors. So what you have right here, this is vector, which means that this v that you see is not just a value, it's a vector. So let's add this arrow right here, and let's add this velocity vector to remind ourselves that this v that we get from this r is also vector functions. Also vector functions. If you diff a vector functions, you also get a vector function. Alright, so this is the first item we learned today, velocity vector. And as you know, vector has both magnitude and direction. The velocity that you get here, this v right here, is going to tell you the direction of its move, of the object, and also how fast the object is moving. All right. Now let's take a look at these four items at the bottom. So right here, number one, it's about the velocity vector, and it's the same thing that we mentioned up there. So let's make a box around this, and I'm going to write the components of this v again. Once again, v here has to be vector, and it's going to be equal to f prime of t I plus g prime of t j plus h prime of t k hat. Alright, definitely what you see right here, vector. Now, the next thing we are going to talk about is the speed. I'm pretty sure that most of you know the difference between velocity and the speed. Velocity has direction, but speed doesn't. Speed is just a scalar, and it only tells you how fast it's going, and you don't know where it's going. So when it comes to the speed, it's just the magnitude of the velocity. So the key word is right here. Speed is the velocity. Speed is the magnitude of the velocity. So if you want to find the speed, you can find it from velocity by taking the absolute value. Speed can be found by taking the absolute value of the velocity. Okay, Now let's move to the next item, which is acceleration. Of course, you have learned this in physics. Acceleration tells you how the speed or the velocity is changing over time. All right, whether it's going faster or it's going slower. So as you know, this is about the change of velocity over time. And this is what you see right here. Acceleration, change of velocity over time. Let's make a note right here. Change, rate of change, change of velocity over time. And once again, this acceleration can be found by differentiating the velocity vector with respect to time. And as you know, when we perform the differentiation on vector functions v, in the end you also get a vector out of this. So what you see right here is not just acceleration, it's acceleration vector. Same here, velocity vector. So a right here, vector, speed right here, however, is scalar. Alright, so now you know what velocity vector is, you know what speed is, you know what acceleration vector is. Now let's take a look at the last one. This is about something a little bit different. So we are going to focus on this v divided by its own size. This vector v divided by its own size. And if you can recall about the topic that we learned on unit vector, we are going to know that when it comes to this amount, it's going to be a vector of length 1 or magnitude 1. So unit vector is a vector with magnitude of 1. Magnitude equal to 1. And sometimes we use the hat notation to represent this unit vector. So here, sometimes we use this v hat equal to vector v divided by its own size. And this v hat, sometimes it can be described as the direction of vector v. Okay, while this absolute value of v can be described as the magnitude of v. And as you know, any vectors out there can be expressed as the product between its magnitude and its direction. So you can express this vector v as the product between its magnitude, which is the absolute value of v, times its direction, which is the v hat. Now let's use what we just learned on an example. So let's move to this slide where we have this one example, and they ask us to find the velocity. Okay, so this is what we need to find: velocity, speed, and we know that is the magnitude of velocity vector. And we also need to find the acceleration, okay, of a particle that moves in the space, and they give us this position vector. So we have this position vector that is expressed in the form of vector functions rt. And as you can see here, we have 2 cosine t, 2 sine t for j component, and the last one is 5 cosine 2tk. The first thing I'm going to ask you to do here is to change this, because this is a mistake when it's typing. So change this to 5 cosine t square. So change this to 5 cosine of t square. And of course, this is k hat. Alright. So I'm going to cross this out. Okay, and then they ask us to sketch the velocity vector at time equal to 7 pi over 4, but it's already shown at the bottom of the slide, so we don't need to do that. The first thing we know about this is the position vector that is given to us. It has 3 components. 3 components means that we are working on 3D space. Alright. And then they ask us to find the velocity. since they give us vector function, the velocity that they ask for has to be vector as well. So this has to be the velocity vector at any time t. We need to find that. We need to find the expression for that. And of course the speed, and it's going to be the absolute value of the velocity vector. And don't forget to leave the variable t here because we need to find the general expression. And of course we need to find the vector function for the acceleration, a at any time. Okay, so let's get started here. So I'm going to write rt again right here. So we have this vector function r of t equal to 2 cosine t, which is the function that explain about the change in I component. Cosine t I hat plus 2 sine t j hat, and the last component 5 cosine t square k hat. Before I continue, I need to clarify that when you see something like this, cosine t square, this is equal to cosine t and overall square, not the same as cosine, alright, cosine t square like this. So keep in mind that it's equal to that, because every year some of you might find this confusing. Alright, so we have this position vector rt ready. So the next thing we can do is to find the velocity vector. And we know that we can find this by finding the rate of change of position vector, which is the first derivative of r with respect to time. So we want to find this v of t and it can be found by finding the first derivative of r. Well, let me put it this way. R of t, alright, and we need to find the first derivative of this with respect to time. And as you know, this r of t is vector function. So we need to apply this differentiation to each component separately, alright? We have done this on Monday, so let's do that again. Differentiate the ft function for I component. So this is I component, 2 cosine of t I, and then plus, and then you diff again, d by dt of the second component, and that is 2 sine t j component plus diff again, d by dt 5 cosine t square k hat. As you can see here, this is like Cal 1. You just need to perform the differentiation 3 times, right? So each one of them is just differentiation with respect to one variable. So here you need to diff 2 cosine t, and I diff cosine t, I get minus sine t. So in the end I have this minus 2 sine t I hat plus diff 2 sine t, I get 2 cosine t. 2 cosine t j hat plus here I need to diff 5 cosine t square, and since cosine t has the square, I need to apply chain rule. So as you can see here, when you look at cosine t square, the most outside function is square. So the first thing I'm going to need to do here is to apply the power rule. So the power is going to come down, and the remaining power has to decrease by 1. So I diff this, 5 stays the same, 2 comes down, and then the remaining power decreases by 1, and I get 1 left. But then this is not just x squared, this is cosine t square, so I need to apply chain rule. I need to diff the inside of this square, which is cosine t. So when I diff cosine t, I get minus sine t. Alright, so this I get minus sine t. Alright, I need to erase this, I need space, k hat. I'm going to write it again here, cosine t square. this square is the most outside function, and it has to come down by the power rule. Okay, so all looks great now. I need to clean this up a little bit. So before I do that, let's take a look here. I have this 2 cosine t and sine t. When I see this, I want to apply one trigonometry property, which is this one. Sine 2t, if you can remember, I think you learned this in high school, equal to 2 sine t cosine t. Alright, so they are going to be equal. And as you can see here, I see the same thing, 2 cosine t and sine t, 2 sine t and cosine t, which means that these terms are going to be equal to sine of 2t. Alright, now let's clean this. Here I have minus 2 sine t, just the same for the I component. Now then next one is 2 cosine t j plus 5 sine 2t, but then I have this minus sign, so this plus in the front I can change it to minus, and the last component is k component. And once again, what we look at here is the first derivative of r, and that's equal to the velocity vector. Okay, so this is the first thing they ask for, so let's put a box around this. Right, we found the first answer, which is this. Okay, let's move to, before we move to the next one, you can see that what we answer right here, we answer in terms of t, which means that we can use to find the velocity at any time, right? We leave the variable intact. So if you want to find the velocity at time equal to 10 seconds, you can just plug in 10, all right? Now let's move to the next thing, which is the speed. And well, we know by now that speed is the magnitude of velocity, so it's not a big deal here. So they want us to find the speed, so speed at any time. So I'm going to put this parenthesis t here. It's going to be the absolute value of velocity vector vt. So all we need to do is to find the magnitude of what we just found, and that's going to be the square root of each component square. So the first component square, I'm going to look at this, minus 2 sine t squared. It's going to be 4 sine t squared. 4 sine t squared, right? Now next component, which is 2 cosine t. And if I square this, I get 4 cosine t squared. 4 cosine of t squared. And for the last component, I take a look at this, minus 5 sine 2t. And if I square that, I get plus 25 sine 2t squared. Alright? Now, at this point, I want you to take a look at this, sine square and cosine t square. I want you to use another trigonometry property, which is sine t square plus cosine, well, let me use the green, that's better. Sine t square plus cosine t square equal to 1. Alright, something old, long, maybe in grade 10 that you know about this. So I'm going to combine these two. Alright, so I have this to combine, and I have 4 as the common factors. So in the end, this is going to be equal to 1, right? So let's combine them. It's going to be 4 times 1. 4 times 1, so I'm going to leave it like this, 4. Okay. You can make a note here, this is equal to 4 sine t squared plus cosine t squared. Alright, and this thing is going to be equal to 1. Now plus the back term right here. Let me fix this. Okay. Alright. Again. Alright, this is better. Okay, the back term, I'm going to leave it as it is. 25 sine of 2t, and don't forget the square. And this is equal to the speed at any time, because we have this variable t in there. You want to know the speed at t equal to 5 seconds, you just put in 5. Alright, and this is the second thing that they want, which is the speed. Okay, now let's move to the next one, which is the acceleration vector. Okay, so we know that acceleration is the rate of change of the velocity. So we have to diff v one time in order to get a. So here we want the acceleration vector a of t, and we know it's the rate of change of v. So we are supposed to differentiate v with respect to time. Okay. So here we have this v right here. So let's take a look here. Now we are supposed to diff this component by component. I'm going to write it again to make it clear to you. d by dt. First component is minus 2 sine t I. Alright. Second component, I need to diff that. And that is 2 cosine t j, and minus last component d by dt sine 2t k hat. Alright, let's do the differentiation here. So here I have this. I need to diff sine, so I get minus 2 cosine t I hat, plus here I diff cosine t, I get okay, sorry, I got interrupted. So back to right here, the second component of the a vector. So we are supposed to diff 2 cosine t here. I get 2 and minus sine t. So here I'm going to put the minus sign at the front. So this has become minus, and this we have j hat. So the last one, I am going to need to diff this sine 2t. Oh, 5 is missing, so let's add 5 right here. Alright, so minus sign still here, and we have 5, and let's diff sine 2t. And I'm going to diff the outside function, which is sine, so I get cosine 2t, cosine 2t, and then I diff the inside, which is 2t, and I get this value 2 out of that by using chain rule. So I get this 2, but I'm going to add this 2 with a 5, so this 5 becomes 10. Alright, so this becomes 10. And that is the last component for the acceleration vector a, and we have this variable t right here. We leave it, and let's make a box around this last answer for this problem. Acceleration vector for this particle in the space. Alright, now some of you might ask, what if I want to find these values at a certain time? For example, what if I want to know the speed at 7 pi t equal to 7 pi over 4? Let's take a look here. What if I want to find the speed at this? T equal to 7 pi over 4. So all you need to do is to apply this. It's going to be equal to, well, let's put it here, speed at 7 pi over 4. It's going to be equal to the square root of 4 plus 25 sine of 2t. So here 2 is going to apply to 7 pi over 4. It's going to be 7 pi over 2. Alright, and also have this square right here. And as you know, this sine of 7 pi over 4, it's going to be equal to 1. Alright, so this term is going to be equal to 1. So in the end, we have this square root of 29, and that is the speed at time equal to 7 pi over 4. So what you see right here is the speed at time equal to 7 pi over 4. And you can do something like this with velocity and acceleration. All you need to do is to put in the time that you want to consider. Alright, so that's how we use the position vector, velocity vector, and acceleration vector, and also the relations between them to analyze any motion in the space. Now let's move to the next application of the vector functions. Here we want to take a look at the initial value problems. If some of you forgot about what kind of problem this is, I want to make a short note right here. It's going to be, well, the essence of initial value problem. When you see this word, initial value problem, I want you to think of this. It's the same as indefinite integration problem. So you see this, you know right away, this is indefinite integration problem. But it's going to be a little bit different from how you just integrate something. In this initial value problem, they are going to give you extra information. So this is what makes initial value problem different from other integration. Extra information. Info. For what? For finding out what the constant c is. Alright? To determine constant c. Alright, recall what you learned in Cal 1. Indefinite integration means that you don't have the starting point or the end point of your integration, something like this. fx, let me change this to black, fx, and then you want to perform indefinite integration. It becomes integration of fx with respect to x and no boundaries. And as you know, when you do something like this, you are going to end up with an unknown constant. This is going to give you unknown constant c. And which you don't know what that is, but initial value problem is going to give you this, some extra info. And it's going to make you be able to find out about this unknown value of c and then complete your indefinite integration. Now let's take a look at how this can be done. So I want you to take a look at the example here. So they give us this acceleration vector, and we can see that we have this for the I component, j component, and k component, definitely something in 3D, and it's accelerating. Now they ask us to find the position vector and this velocity vector. So let's take a look at the flow here. They give us the acceleration. They want the velocity, which means that we need to integrate a, right? Integrate a in order to get velocity. And once we get velocity, we need to integrate v again to get the position vector. And each time you integrate, you are going to end up with this constant value c. So without any other information, it's an unknown. And we don't like that kind of that form. So initial value problem is going to give us this extra information about some points on R and V. So let's take a look at the first point here. So this extra information is right here. extra information, extra info, is the value of position vector at time equal to 0, right? Notice here, time equal to 0, and also velocity vector at time equal to 0. This is the extra information. So I'm going to add it right here. Position vector at time equal to 0 is going to be equal to this, 3, 0, 0. And the velocity vector at time equal to 0, this is equal to 0, 0, and 0. If I translate this position vector 3, 0, 0 as coordinates, it's going to show up right here. And these equations are going to explain about the motion in the space. Now, keep in mind that these two are the extra information for us to complete the integration without leaving any unknowns, right? So for C. Okay, now let's take a look here how it's done. I'm going to start with what is given to us, which is the acceleration vector, which is this. Vector A, t, equal to minus 3 cosine t. I, minus 3 sine t, j, plus 2 k hat. And they want us to find the velocity vector. So we know that the relation between acceleration and velocity is one differentiation or integration. So v that they want, vt, is going to be equal to the integration, right? We go backward this time. Integration of the acceleration vector function with respect to time. Now, what we are going to have to do here is to apply this integration to each component separately. All right? So, what about I do it directly without having to write it again? So the first thing I'm going to do here is to apply this integration to the first component. All right. Well, let me write it, otherwise it can get confusing. So here I'm going to integrate the first component, which is the minus 3 cosine t. Integration of minus 3 cosine t with respect to time. And that is the first component, I. Okay, now integrate. Next component, minus 3 sine t with respect to time. And that is j component. Okay, and last component, integrate 2 with respect to time, k component. So here I have this integrate of minus 3 cosine t, so I integrate cosine t directly. Integrate cosine t, I get sine t. So in the end, I have this minus 3 sine t. I need to save some space here, so I need to squeeze in. Right. So here I get minus 3 sine t. Right, go backward. Cosine t to sine t. And this is the first component. Right, next one, integrate of minus 3 sine t. So I integrate sine t directly. Integrate sine t, I get minus cosine t. With the minus sign in the front, this becomes plus 3 cosine t j hat. Alright, now I need to integrate the last component, which is 2. So this becomes 2t. This one is easy. K hat. And this is velocity vector. What we just did here is indefinite integration. Make a note here, indefinite integration. Which means that we are going to end up with a constant in the end. Alright, so this thing is missing, which is plus constant. Recall what you learned in the first place when it comes to integration in Cal 1. You integrate something, you always get this constant. Why? Because if you diff this, v. This constant is going to go away. So it has to come back when it comes when we perform the integration. Now, with this constant appearing here, I want you to take a look a little bit further. So before we consider this c. Let's take a look at this v. We know that it's a vector. So what you get right here is a combination of three components, right? It's on its own, it's a vector. So what we have for c right here, this cannot be just a constant. It has to be a full vector as well. So let's put a vector sign right here that the constant that we get here is a vector, and I'm gonna make this 1 as the first constant. So make a note here that this is vector constant. In Cal 1, the c is a scalar, but here we work on vector valued functions, so c here has to be vector as well. Now, right, we get v right here, and it's not complete because we have this unknown constant c1. Our job is to find out about the c1, and how do we do that? We use the extra information that they give to us, which is this. They give us the velocity at the beginning of time, t equal to 0. Oh, by the way, the reason that they call it initial value is because they usually give the value when time equal to 0. At the beginning of time, initially, what value of v is. So if we know that, we can use it. So the first thing we know is that the velocity vector at t equal to 0 is this 0, 0, 0 right here at the top. And we are going to find out about this with the equation that we just found down here. Let's use this equation to find out about this v at time equal to 0. So I'm going to continue this. V at time equal to 0. So here, all I need to do is to apply 0 into this equation, and I get sine of 0, and that's going to be equal to 0. So I get 0i plus 3 cosine 0, which is 3j, and last one, plus 2t, which is 0k. Right, now t equal to 0. Right, this 0, this 0, and this 0. And I get what you see right here. And let's, oh, don't forget this c1. c1 vector. Okay, now let's change this into the vector form. This is going to be 0, 3, and 0 plus vector c1. And it has to be equal to what is given to us. Has to be equal to this. Alright, so we have this. Has to be equal to 0, 0, 0. Now all we need to do here is to balance this equation and find out about the c value. So here, let's take a look here. This is going to be equal to 0, 0, 0. So I need to move this vector 0, 3, 0 to the other side, and I can solve for c1. Here I get c1 to be equal to. So let's solve it right here. c1 equal to 0 minus 3 and 0. So what I just did is to solve this equation. I move this vector to the other side, and that's why it becomes minus 3. And since I know the c1, I can complete this vector this vector function vt. Alright, I'm going to complete this vector vt. So I'm going to replace this unknown with this new vector that I just found. Since I know that c1 is equal to 0 minus 3 and 0, I can use it. So this is going to be equal to 0 minus 3 and 0. Right? So let me complete it right here. I'm sorry about the space, but I need to save it. So I'm going to put the final value of Vt right here. Vt equal to, first component, I used to have this minus 3 sine t. With this extra term 0, is nothing changes. So I have this minus 3 sine t I, right? Now, second component, I used to have this 3 cosine t, but then I have this extra constant, minus 3. So I'm going to have this plus 3 cosine t minus 3 I. Oh, j, I'm sorry. And for the last component, I have this 2t plus 0. So plus 2t k hat. Alright, and that is the final answer for the vector functions for the velocity. So in the end, I just need to add this constant right here at the j component. Alright, the rest is the same because c has nothing on I component and j component. Okay, so let's write it again here because we need to use it. Vt, the complete one, is equal to minus 3 sine t I plus 3 cosine t minus 3 j hat plus 2t k hat. Alright, so that is the first answer, but then this is not the end because we are supposed to find this position vector r of t too. So we need to integrate this velocity vector to get position vector. So they want us to find this r of t, and we know this can be found by performing integration on the velocity, and here we perform the indefinite integration. Alright, now let's do that. We are going to perform the integration on each component of v separately. So first component, integrate of minus 3 sine t I. Oh, don't forget dt, I'm sorry. Put dt in. I plus integrate of the whole thing, 3 cosine t minus 3 j, dt j hat, plus last component, integrate of 2t dt k hat. Now let's continue this. Integrate of sine t, you get minus cosine t. So here becomes 3 cosine t I hat plus integrate of 3 cosine t, you get 3 sine t. 3 sine t. Integrate 3, you get 3t. And you have minus in the front, and all of them for j component. And last one, you integrate 2t, so you get 2t squared over 2, 2t squared over 2, and these two cancel. So I'm going to take it out, these two. So in the end, you have this t squared, and this is for k component. Alright, and once again, we just perform the indefinite integration, which means the same thing is going to happen. Indefinite integration. This is going to lead us to an unknown constant. And keep in mind what we just have right here is a vector. They come together. So the constant that we have right here has to be a vector as well. And we are going to call it C2. So this C2 comes from the integration. And we have to find out about this by using the information that they give to us. And that's going to be this one. Position vector at the beginning of time, the initial value of the position vector. So we know this value up here at time equal to 0. So let's use the equation that we found down here to find the same thing. Alright, now what we have right here is r of t. Let's find out about this r of 0. So I'm going to input 0 into this equation. The first term I get 3i. Alright. Next term plus, well, 0, right? This 0. And this 0. Also this 0. 3 sine 0. Sine 0 is 0, so I get 0. And the next term is also 0, so I get 0j. And plus, last term also 0k. Alright, and in the end, plus vector unknown vector constant, which is C2. C2 unknown vector constant. Okay, so here let's combine them. These three, they are together, and you can see that this is 3, 0, 0 plus this vector C2, and it has to be equal to what is given to us, which is here, R0. It has to be equal to this 3, 0, 0. And if you balance these equations, you are going to get this value of C2 to be equal to, from this, you are going to get C2 to be equal to this vector 0, 0, and 0, right? Because these are the same. So in the end, C2 has to be 0. Now, once you get this C2, you are supposed to put it back to complete the vector functions r of t. So I'm going to erase this, right? What about I write it again right here, C1. From this, you get C1 equal to 0, minus 3, and 0. And I'm going to need this space. Okay? Now, let's complete this vector function r of t. So I'm going to come back to this line. Okay? And I'm going to add this 0, 0, 0 right here as C2. So instead of unknown, I know right now that it's this. Right? So this means that nothing changes, right? So we can just neglect this. So in the end, we have this RT as a complete function. First component, 3 cosine t. Nothing changes. 3 cosine t. 3 cosine t I plus next component, the same thing, nothing changes. 3, oh no, right, too many colors. 3 sine t minus 3t j, and the last component we have this t squared k hat, right? So last component plus t squared k hat, t squared k hat, and that is the complete vector functions for precision vector.